This is Ayush, and today we are going to discuss find the minimum element in rotated sorted array problem. And this is Leetcode 153. Uh, this problem is like very interesting, and this can be solved by binary search. So why you'll get this? So let's read through problem and see what we can do. Suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, an array nums 0, 1, 2, 3, 4, 5, 4, 5, 6, 7 might become this if it was rotated 4 times, and if it was rotated same 7 times, it would be the same. Uh, Notice that an array this like a of 0, a of 1, 2, a of n minus 1, rotating this array one time results in a of n minus 1 to shift backward. So this is the definition of rotated. I'll explain it as well. So given a rotated sorted array nums of unique elements, return the minimum element of this array. You must write an algorithm that runs in O of log n time. So this is your hint that you should apply binary search here. The problem explicitly states that you have to give an algorithm which runs in O of log n. Other than that, constraints are just not necessary here, as the problem explicitly mentions the complexity. Okay, so without further delay, let's see what how do we deal with it. Let's see what is a rotated sorted array. uh I think everyone knows what is a sorted array, so we'll take the same example as in the problem. So this is 4, 5, and what was it, and 6, 11, right? Okay, so this is our normal sorted array, right? So like it is increasing, and in this case, so what does rotated sorted array mean? So what does it mean? Basically, what are we doing? Let me just erase it. This is our normal sorted array. As per definition of the problem, if I rotate it by one, if I rotate it by, let's say, one element, then 7 comes here. Alright, and let's write without commas actually, so things would be more clear. We have 0, 1, 2, 4, 5, 6, 7, right? So if I rotate this array, this is normal sorted array. If I rotate this by 1, the rightmost element comes to left side, the beginning side. So this 7 comes here, right? If I rotate this by 2, then 6 comes here. Let's shift this actually to, yeah. Now if I rotate this again, now rotate by 3, then this comes here. If I rotate by 4, this comes here. So for every rotation, what I'm doing is picking my last element and bringing it to front, picking my last element and bringing this to front. So when we rotate the array 4 times, you'll get this. So that's just the basic definition of rotated sorted array. You get that by clearly using problem statement as well. That was just rotated sorted array. And now, as problem told us how to find minimum, and we have to find minimum in it. So if it was a normal simple array like this, normal simple sorted array, so you clearly know that without applying any search or anything, you just know that your minimum is this, right? The 0th element is of course minimum in sorted array. So but in this case, can you tell that the 0th element is the minimum or not? No, it may be minimum, it may be not. Like, if, as I told you, array can be rotated 1 to n times. So n is basically size of array. In this case it is 7. So if I rotate this 7 times, as you can see, this comes here. Okay, just this comes here, this comes 3 times more, this comes here. So we will get original array again, right? So if I rotate the 7 elements array 7 times, each time I'll bring element last element to the front to the front again, then what you'll get is the original array itself. You can try this on pen and paper, it will be very clear. So other than that, okay, now let's see. So you cannot guarantee that the minimum element lies on the first 0th position, but it may be minimum, it may not be. So we need to search that. So the brute force approach is simply we can do a linear search, a simple linear search, in which I'll go through each element and track the minimum. Is like I'll just go through each element, 4, then 5, then 6, then 7, then 0, and I'll keep a track of minimum in variable minimum. This would be something like just min of nums of I. Yeah, this right. So we can do this using linear search, but problem explicitly mentions that we need to do in logarithmic time, and it's fast. So uh to do it, like, to apply binary search, one observation that I always use is not the sorted is one thing, but the thing is, you should know when you can eliminate the half. You have a search space in binary search, you need to know when can you eliminate one half. If you are able to successfully eliminate one half in each iteration, you are able to successfully implement binary search in that question. Remember this point correctly. So in this case, let's try to actually make the graph of this array, right? uh it would look something like, let's draw it like this. So in our x-axis we will have our index, and on our y-axis we would have our nums of index, the value. This is our nums array, let's say. So let's draw the graph. So it would be 4 here, that's 4, 5, 6 and 7, let's say, right? I'll draw a rough graph here. So it would be something like this, right? Yeah, so this is 0th index, this is the first index, this is the second index, and this is the third index, something like this. Yeah. So for other elements, like this is my 0, 1, 2, 3, 4, 5, 6. Let's draw the remaining graph as well. Let's say we have 4th index, 5th and 6th. So the graph here would look like this: 0, 1 and 2. So I'm roughly drawing it. So this is 0, this is 1 and this is 2, right? Yeah. So the normal sorted graph, if array was completely sorted, not rotated or anything, we know that it would look something like this, right? Simple monotonic graph. But now the array is rotated as well, but we have advantage that it is sorted. So now how do we apply binary search? First and foremost, we would have a search space. Defining search space is the first thing you do in binary search. So this is your low, this is your high, and you'll have some mid. So low of course would be the beginning of the array, so it would be here at 0th index, let's call it low, and this is high. Okay, so now you have some clue that we are dealing with finding minimum, right? So, and also this halves look kind of something you can deal with. So let's make cases, and how can we eliminate half would be decided on those cases. So let's say that mid comes here, somewhere here, right? If mid is here, now I know that my nums of 0 is less than mid, right? If my nums of 0, like, we lie in this portion of the graph, now my nums of 0 is less than mid now, then I know for sure that I lie in left half of my array, left half of my rotated sorted array. So this is the left half, and I know for sure what is our goal. Our goal is to find this element, this one element, which is minimum. In this case it is 0, but you can find index as well, no problem. You have to find here, and you can clearly see from this graph, and always you can confirm that graph of a rotated sorted array would look something like this. You can confirm this. You can just write some examples and check for yourself. So our goal is to find this element. Which is basically the first element in right half of our array, right? So if my mid lies here, which is greater than my nums of 0, then I know for sure that I'm in left half of the array, and I need to go to right half. So for that, so I'll just write pointers here as well to just make it clear. So this is my low for now, and this is actually high, right? Let's write it somewhere like this. Yeah. So I know for sure if my minimum exists, like something minimum than nums of 0 exists, then it would lie in right half. So I can eliminate the left part now. I can eliminate the left part. So I know for sure that my answer does not lie here. So I can eliminate this. I can eliminate this, and just I'll how to eliminate the left half? I'll just make my low pointer to be mid plus 1. Now low would be here. Let's erase our previous mid now. Right. Now my mid would be, let's say, somewhere here. Okay. Now my current min, I have tracked is here. Like I know now my 4 is like nums of 0. This one was my current min, and the nums of mid I found uh basically is, let's say, 1, right? So I know that my nums of mid is now smaller than nums of 0. Nums of mid is like smaller than nums of 0 because that's clear. So I know that I lie in right half of my array, the right half of my rotated sorted array, right? If I lie on right half, like all the elements in the right half, as you can see from the graph, all the elements in the right half are smaller than my nums of 0. So these are all potential candidates for my minimum element, right? So this can be my answer. I'll store it. This of course is lesser than my current minimum, which is nums of 0. So I'll store it, and I know that here the elements like greater than mid and between mid to high are greater than mid. So instead of like traversing here, I'll eliminate this half. I can eliminate this half. Make sense? We are trying to find minimum. We are trying to find this pivot. Always remember, we are trying to find this pivot. So we are taking conditions on how can we eliminate halves. So you know for sure that you can now eliminate this half because every element which lies to the right of mid and high in the second half, the right half of the array is always greater. So you don't have to search there. You just have to search, okay, I found the current minimum here, something smaller than nums of 0. So now if something more smaller exists, then it would exist to left part of left part of mid. So what I'll do is trim my search space down. I'll just eliminate this half. To eliminate right half of the search array, I'll just move my high pointer to be mid minus 1, which would be somewhere here. Let's remove mid as well, or high would look somewhere here. And this is how the intuition works basically, right? And now your mid would be this, and you would do the similar thing. Now I just explained this by graph. I'll try to explain this using our array example as well. So this graph was just to give you intuition of what I was thinking while solving this problem, and how you can think of this idea as well. So let's take the same example now, writing it more briefly and like explaining it in more correct way, more better way to understand, just by looking at our indexes instead of graphs. That would make things more clear, like how are the pointers moving. So we have 4, 5, 6, 7, 0, 1 and 2. Okay, and this is our nums. Let's write our indexes as well. This is 0, 1, 2, 3, 4, 5, 6, right? So now this was our low initially, and this is our high, and our mid would be what? This, right? So this is our mid. I can see that my nums of mid is greater than my nums of 0. That clearly means, as from the graph as well, that clearly means I lie in left part of my array, right? So if there exists a minimum which is smaller than nums of 0, it must lie in right part. So I must go to right part. So what I'll do now is eliminate this half and go to right part. So how would I eliminate? I can just move my low pointer to a mid plus 1. So I have successfully eliminated one half. Will I be able to do it again? Yes, again I would be able to do it again and again. This is just based on intuition which we derived from our graph. So now this is my low, this is my high. uh, my mid would be this, right? So yeah, now our nums of mid, like nums of mid is 1 and nums of 0 is 4. Our reference point is nums of 0. So I can see that my nums of mid is smaller than nums of 4, like nums of 0. So my minimum I'll initialize initially to 4. It was initialized to 4, like which is nums of 0. And when I find something smaller than it, I found something smaller than it on my mid pointer, right? So I'll update it to our new minimum, and I know that now this is like minimum, but can I eliminate one search space, one half of the search space? Yes. I know that everything greater than here, like this is 1. I know lie in right half of my search space now. So I can eliminate everything to the right here, because this is minimum and everything to the right would be greater than this. I don't need those elements. I need something smaller. So I'll search in my left half of the current search space. So to search in left half, I'll update my high pointer to be mid -1, which is here. Now low would be this, as low and high would be this, and this is mid as well. Now I'll check again. Is my nums of 0 less than is nums of 0 greater than my nums of mid? Yeah, nums of mid is smaller. So I'll update my minimum to be 0 again. And now if I know this is like the pivot element, this is the minimum element, we found it, but just to now our binary, we have to still eliminate something to like terminate our binary search. So let's say we are in right half, right? So if there exists one more element which is smaller, I'll have to search left. So I'll eliminate the right half and move left, search in left half. So I'll just update my high pointer to be equal to mid -1, which would be this. Pretty clear. And as you can see, we have like exhausted our search space. So binary search terminates and we got a minimum, right? I think we can take one more example to make things clear. So actually, yeah, like if you can just, if normal also, if array was rotated n times, let's say, if it's looking something like this, 11, 13, 15, 17, right? This is your 0, 1, 2, 3. Initially your min was stored to be 11, right? Nums of 0, we are assuming that our minimum is nums of 0 for now. So we'll do the same thing. This is our low, this is our high, this would be our mid, right? So my mid is greater. Now I can see by naked eye that this entire array is left half. The left half, the one we discussed, the left part of the graph, basically this array does not have a right part. So now I can see my nums of mid is greater than my nums of 0. So that to move to the right half of the array, I just need to eliminate my left search space. So I'll eliminate this this search space. I'll move my low here. So this is my new low, this is my new high. I will not update min as I didn't find anything which is smaller than my current min. So now again I'll do binary search. This would be mid again, and again you can see that my nums of mid is not is just greater than my nums of 0. So I'll again search right. So again if I search right, I'll not update the minimum. So again if I search right, I'll make my low pointer to be mid +1, which would make here, and the mid will be also here. Again I'll see that okay, my this nums of mid is still greater than my nums of 0. Still I'll search right. So this would make my low here and high here. So that this just terminates my search, and we didn't update minimum, which is fair because nums of 0 itself was minimum, right? Pretty simple. You try to take this example or some example similar to this, try to do it on pen and paper, then things would be more clear. Moving on, let's move to the pseudocode. So let's initialize our int in pointers of binary search as low and high equal to 0 and n -1, where n is size of our array. We'll write the same condition while low is less than equal to high, I will calculate mid equals to low plus high minus low by 2. And now if basically also we'll initialize here our minimum to be nums of 0 initially. Okay, and if I see my nums of 0 is, let's say, lesser than or equal to my nums of med, this basically means that I lie in left half of my search space, which is like greater. So my minimum element lies in the second half of our rotated array, if the second half does exist. So I'll move my search space to right. I'll eliminate my left search space, move to right. So how I can do it? Just updating my low pointer to mid plus 1. Else means that my nums of 0 is now greater than nums of mid. So I found something smaller. So now I'll update my min to be nums of mid. You can do minimum function as well, but I know for sure that like every time I move, I'm moving closer to my minimum element, so I don't need to check it. But you can try this on pen and paper, you will get why I'm doing this. Then yeah, you'll update your min, and now you know that you are in a right half of your array. You're here now. Now you can eliminate the right half of this second half, like this part. You are in this part now. You would be successfully eliminate this half, correct? Because you know for sure that every element now would be greater than nums of 0 in this, like would be greater than nums of mid in the right half. So you'll eliminate the right half and you'll search in the left half, so that for doing that you need to update your higher pointer to be mid minus 1, and that's it. You'll just return your minimum element. Amen. So yeah, this is a pseudo code, and to yep, let's write the code now. So let's write the code in C++. We'll do similar to pseudo code. We'll initialize our low pointer to be 0, or high to be nums dot size minus 1. Let's initialize our min to be nums of 0. If minimum like does not exist, then the 0th element is minimum. Other minimum does not exist, right? I'm assuming that my 0th element would be minimum. Now let's apply simple binary search. This is my condition, and let's calculate mid to low plus minus low. To prevent overflow, you can check why are we doing this. And now if my nums of 0 is less than equal to my nums of mid, so this means I am lying in this basically means if minimum exists, we need to search right. Okay, we need to move to right half. So I'll just update my low equal to mid plus 1. Else I've found something. Now my nums of 0 is greater than my nums of mid, so that means I've found something smaller, so I'll update it. So I can just do nums of mid, and to be sure you can do this just to like have the sense of minimum. But do you actually need this? Think about it. You don't need this, because we are actually trimming down our search space, which is closer to minimum. You will never encounter an element which is greater than minimum in this else block, so you don't actually need this. So I'll just keep my nums of mid here. You can think about it. And now as you can see, like this is the condition. This means that if something smaller exists, something more smaller exists, it must exist in left, as we are in the second half of our search space. So I'll just do, so So to move to the left half, I need to eliminate my right half. I'll just do a high equals to mid minus 1, and that's it. I'll just return min. This should run fine. Yep, let's submit it. Yeah, that's it. As we are applying simple binary search, this is of complexity of login, and we are not using any extra space. We are just using constant space, so the space complexity is of 1 as well. So yeah, that's it from my end. If you have any doubts or anything, just comment it out. This was my way of doing the problem, and hope it was intuitive to you as well. Thank you.